So now all this while, what we have been doing is our linear models. We started off with linear regression. We did classification we did both regression problem and classification problem. Today, what I'll try to do is we'll do say classification and also we'll generalize that to regression problem. We'll getting into non-linear models now. So the idea is till now we have done linear regression, which were all linear models. We had done SVMs with great detail, which was again a linear model. But these models can only be used to categorized elements or when they are linearly separable or when the data is a linear combination, whether if it's a regression problem, the Y is a linear combination of the labels. We also saw the variant where we could address non-linearity in the data by using what is called as a kernel, right, in SVM. So using kernels, we could address the non-linearity in the data, and then we could use that non-linearity to uh, to address functions like circles that we saw last time. Right? But today what we'll try to do is we'll try to take this one step forward where we can give you any general function and that model would be able to learn that function. It will not be dependent on uh, the algorithm that you're using as such, but on the a general class of functions which would be which would actually be composed of many small individual perceptrons, which will be seeing what are perceptrons, individual modules called perceptrons. So the motivation for perceptrons comes from the idea of neuroscience itself. So where in every one of us, what happens is we have neurons in your brain and electrical or neurotransmitters. So neurotransmitters from these synapses come through your dendrites, if you recall your class 10 biology. And then those neurotransmitters are used to do some computation. So each neuron would have multiple synapses from many different other neurons. And those would be used to do some computation. And it would decide whether to spike or not. What does a neuron do? A neuron would put an action potential. So this is called an action potential, which is also called a spike. So where you release a neurotransmitter, if it is a either it can be excitatory or inhibitory, you release that neurotransmitter, it goes through this axon and then goes to the next neuron. And this goes on through the entire brain of us, and that is the basis of all the decisions that we make. So Rosenblatt in 1958 to 1960 uh, converted this entire idea into mm, a mathematical model, which he named as a perceptron. Why? Because it is able to perceive information or stimulus from the stimulus, which are inputs to the neuron that are normally through dendrites in a biological neural network. And then that is used to compute a variable y, which is a signal which you are trying to. So whatever you are passing through the axon down to this um, through this axon into the synapse is the signal y. So till today, what have we done? We have done only new linear models, right? So today we'll also start off with a linear model and then see how it. So the brain is very highly a non-linear. So we'll start off with a linear case and then we would generalize to a very complex non-linear case. So the first model is called the perceptron model. So what does it do? So it does something like this. So whenever it reaches a threshold, just like I told you in the biological neural network, say the threshold is t, it starts giving you an output. That is y is equal to 1. Before that, it doesn't give you any output, or we write this as y equal to -1. We'll see why it is useful to write that as y equal to 1 and y equal to -1 respectively. So is the formulation clear? So if it is a linear model, do we know a way to do this where we would be able to assign a positive value to a above a threshold and a negative value below a threshold? So you already know that. If you recall, you have, say, these are your positive points and the reds are your negative points, right? Using these greens and the reds, So what would be an ideal model that would give me +1 for the greens and the -1 for the reds? So for example, so your here this decision means, here threshold means that you have a signal, say. So this is a signal, say, or this is the class that you care about. So to say that it belongs to that class or output y equal to 1, what would be a best model that you can do? So first I'll ask you this simpler question. So this is linearly separable, right? So if I have a hyperplane that is separating them, so do you agree that one of the class will be W transpose X positive plus B, say, will be greater than 0? For example, we are taking one of them will be positive and one of them will be negative. We're taking this side to be positive and this side to be negative, right?
Yes.
So one of the class will be positive, one of the class will be negative. Other would be. So we have done this, right? We have done this in SVMs and so on. But in SVM, we make it even a stronger model where we put a margin to it, greater than 1 and -1. In the perceptron algorithm, we don't need to put that margin. We'll see later on why. Here you just have a weak margin classifier. You have any hyperplane that separates. Your idea is to have a hyperplane. Unlike SVM, the best hyperplane, here you can have any hyperplane, right? So give me one intuition. So how would you penalize the model? When you train the model, how would you penalize it? That's the question that I want to ask. So first tell me what would be the output. So your output, your decision would be, do you agree? This will be sine of W transpose X plus B. Your say H of X, which will be plus or -1, right? Yes or no? So
Yes.
if it is a positive case, if it is greater than 0, it will return 1. If it is less than 0, it will return -1. If any case if you do not follow, please interrupt me. One is +1 and another one is -1. And this W is the design parameter. For the time being, let's do something. Let's do that a little bit later. Okay. So this is your model, sine of W transpose X plus B. But then how do you learn the model is the question, right? So you have to give some loss. We have seen that we have to give some loss to the model to be able to learn, right? So that we get the desired properties. So the loss that we will define is, what should be the loss? You tell me. Tell me. If you make a misclassification, so there will be two cases, right? If I make a misclassification,
Like maximizing the distance from the points.
in the good, that is true. From the hyperplane, you mean, right?
Yes, yes.
Yes. So the idea is if I make a misclassification, for the time being, we are considering only linearly separable case. If we make a misclassification, tell your friends to look at this video. It will be very useful later on. So if I make a misclassification, what will happen is I want to penalize the model so that it learns, right? So what will I do? Say I have a red point somewhere over here. So what I'll do is, so do you agree that if I have a distance, a measure of distance, this is a distance, right? So if I have a red point over here, this is a misclassification. So this is the distance. What is the value of the distance? We have found this in the optimization class. What is the value of a distance from the plane?
Like
Minimum distance.
that norm of that to omega tx plus.
W omega. So it's, you just put the value of X and divide by the norm of W, right? So for a plane, it is ax plus by plus c by a square plus b square, right? Cz plus minus d by a square plus b square plus c square. This is what we found, right? In 3D.
Yes, yes.
We found this last time. So this is nothing but W transpose X plus B. So this is the distance from the point to the plane. So now I tell you for an optimal classifier, W star is equal to 1. So I will, at the end of the day, I will normalize it, right? So therefore my distance of X is proportional to W transpose X plus B, yes or no? Distance from the plate. It is, if you are ignoring the constant of the norm of W for the time being, right?
Yes.
Why am I doing this is, do you agree the greater this is, the farther the point is from the plate? Greater means farther the point from the plane, right? Do you agree? For the greater the value is, the farther the point is from the plane.
Yes.
So what would you like to do in this case? So if it is already in the correct class, then you don't want to penalize the model. That's the idea, right? So the idea is zero loss if your d of x or sine of W transpose X plus B is equal to Y. Yes or no? If it is equal to the word, equal to the label Y. So if you're thinking what is X and Y is the data set that I have, right? X is the training examples, which are the features that we have seen till today, like iris, petals, and sepal length, and Y is the label, right? Any questions? Same notation as the SVM classifier, right?
Yes.
So for this case, I'm going to not penalize the model. So I want it always, I want these points to be away from the hyperplane in the correct direction. So I'm not going to penalize it. But if it is in the opposite direction, what will I do? If Y into W transpose X plus B is less than 0, right? This is also meaning Y into W transpose X plus B is greater than 0. Yes or no?
Yes.
If the both the signs match. If it is less than 0, I want more penalty for points away from the plane. Yes or no? So should be proportional to dx. Do you agree? Or I'll just write dx. If the distance is higher in the wrong direction, I want to penalize the model. Yes or no? I guess you understand that. If you are not, please stop me and ask.
Means suppose we have wrongly classified a point. So
Yes.
then you are doing the loss function. So then you are means
Trying to
can you
minimize
explain?
that. Minimize the distance. Loss is like what you will try to minimize, right?
Yes.
You want to put a penalty on the model for putting a negative point very far away from the wrong direction, right? But
Okay.
not
Yes.
so much if it is very close to the line. So if this is positive and this is negative, and I have a negative point over here, I will give a low penalty. Positive plane, positive side, negative side. Versus if I have a negative point over here, I give a high penalty, right?
Yes. Understood.
Because the worst case, what will happen is you will just misclassify the positives to be negative, negative to be positive. Then in that case, you want to just change the y's like that, right? So you would not try to, you will only try to penalize the negative classification. So this you can write, this is the same as the SVM model. This is also called the hinge loss. We have seen that last time. So the loss that I will write is again a function of W is the max of 0 comma you. Now you tell me if it is, if you understand. Take a moment. I will not like feed you through this. Say you have n data points, or let me write I, it's easier to understand, right? The idea is very simple here. So whenever there is a misclassification, right? Do you agree that dx is equal to w transpose x plus b? Right? That's how we defined it. Assuming that w star. So this is one of the relations that I'll be using. The optimal w has norm 1, right? Or wherever w you have, you can always normalize it. That's the idea, right? Okay.
Yes.
So now so that is w transpose x plus b. So now if you are misclassifying, you want to put a loss. So do you agree that this will be negative when this part will be negative when misclassified, right? Yes or no?
Yes.
So minus of w transpose x plus b will be greater than 0.
Okay, then that value will be taken instead of 0.
Exactly. So if it is misclassified, you take this value, correctly classify, you take 0. Now it is very simple. Since we have developed the math of this, it's very, very simple. So the algorithm that you have in the perceptron algorithm is very, very simple algorithm. It's the simplest you can find. So you take data points from the sample. So you can just read this. It is not even difficult. So for the time being, what I'll do is I'll write xi as 1 comma x. This I have already been doing, right, throughout my classes. So then I can write w transpose xi plus b as simply 1 comma w or w0 comma w into xi, and this I'll be writing as w. Okay, so instead of writing w transpose x plus b, I'll just write w transpose x, because I can always put the constant in, right? Just putting a 1 and a w0. Okay,
Yes.
so my equation becomes, so the algorithm says pick a point, pick one point. If misclassified, train the model. Else, pick another point. This is the algorithm. So you can see I've written it on the left, given a data set D and a W0. So I have written, so you have a W0, which is starting randomly initialized W. You can also start from zeros, no problem. You pick a data point, right? And then if this is less than 0, you do the update. We'll see how you do the update. Right? Let's see. So how will I do the update? Say one data point I pick. One data point. One point. Say name it as xj comma yj. So now tell me, what are the possible losses? Loss for the data point. So I'll name this as x p. So loss for p, what will I get? For the pth point, what is the loss I'll get? I'll get 0 loss if yj into w transpose x I is greater than 0, right?
Yes.
Remember this max.
So why it is xi, xj it would be the.
Yeah. Maybe misclass. I've just miswritten. Uh, or it is yj w transpose xj if yj w transpose xj less than 0. Yes or no? No question. Is there any doubts? I hope no. So now, how do you do? How do you learn? So you do. I have taught you gradient descent, right? So I'll just put t plus 1 on the bracket on the numerator. So I will take, so this is the gradient descent step. What will I do? Minus eta times dl dwt. Yes or no? Do you agree?
Yes.
Tell me then, what is the value of dl dwt? dl dw at w equal to wt. What is the value? 0, it's a constant. If yj wt transpose xj greater than 0, else what will it be? Take the derivative, simple. So w transpose x ka derivative, what is the derivative of w transpose x with respect to w? Partial derivative. Recall what have we done? What is the partial derivative? It's the derivative with each component, right? Yes or no? So this is nothing but x. Any questions? What is w transpose x? wt transpose x, whatever w transpose x, w1 x1 plus w2 x2 dot 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 wn xn. Yes or no?
Yes.
Now I take derivative with each component. What do I get? w1, sorry, not x1, w1. I get x1. Yes or no? We have derived this 3-4 times before. Clear?
Yes, yes.
So I just get the x vector, whatever was there. So I will get minus yj xj. Yes or no? Correct? For every misclassified point, we will have this, correct?
Yes.
Therefore, you will have wt plus 1 for all misclassified, for a misclassified point. You will have wt plus 1 is equal to wt plus, in this algorithm, eta is set to 1 plus yj xj. Do you agree? And that's what I've written. So B I have written separately in this case. You can also correct it and write it together as I have written now. Okay. This is the same thing, right? In this case, it is 1 instead of x value. So you can club these equations together also. Clear? For every wrong class, you are going to update this. Okay. Any questions? We'll do an example now. If there's no question, we can go to the example.
Could you explain there a graph you had drawn before of signals and y plus 1 and y minus 1? That I
Yeah.
couldn't get.
So anytime you have, the idea is you want to classify a positive a data point, right? This signal, this graph, right? We have understood the algorithm and the math that I have done, right?
Yes.
So what do we feed into the model? So if you have a neuron, the neuron say has to categorize between Coke and Pepsi, Coca-Cola and Pepsi, and Coca-Cola is say 1 and Pepsi is -1. So you taste the Coca-Cola and you have the stimulus given to you, right? And then your neuron does that computation. So if it is after it reaches 0, it gets positive feedback for positive response for Coca-Cola. Yes or no? Once that output, whatever signal, say W depended on some features X, say the sugar quantity is the feature, right? If that sugar quantity was above a particular threshold, then only you will get 2 greater than 0. That's the idea. So this is the value of y, W transpose x plus b. This is x. X is the feature, right? And you can just take ax plus b.
Like here, W and B are all learned by the neuron.
Exactly. W and B biases and the weights are learned by the neuron. So we are learning them, right? We saw that. So the neuron has predefined weights, which is weights that weighs those inputs. We'll see how it does it just now. But the idea is whatever input you see is sugar quantity, the amount of carbon content, amount of carbon dioxide, all of them will be weighed by these weights. And then it will take a decision, like based on what is the sign of the ax plus b. This is a very simplified model. In case of neurons in the brain, you have a lot of complicated things going on, right?
Understood.
But this is exactly what happens in the brain. So therefore, the neural networks are called to, and it is seen to modulate different regions of the brain, like CNNs and all look like the visual cortex and so on.
Acha, and one more thing, y equals to -1 was the normal one, and if any change is made, then it becomes y equals to 1. Means
Y
why did
equal to,
you?
it's just a convention. So generally in signal detection theory is the theory that is used to see signal versus noise. So generally you have to say you are favoring one class, say cancer versus no cancer, say Coca-Cola versus no Coca-Cola. So no Coca-Cola is the other class. That's the idea. So therefore, to get in favor of your favorite class, that's the convention that is used to make you understand that. Clear?
Acha, okay.
Because whatever class you like is called the signal class in signal detection theory. In signal detection theory and also estimation theory, whatever class you like is called a signal class. Whatever you don't like is called a noise class. So the idea is something like this. I'll just show the brief diagram for that. So this is a distribution of signal class. This is a signal distribution of noise class, signal class. So after a particular point, you will be deciding that it is a signal class or not, right? So these are the features. So say it has a sugar content. So sugar content, less sugar content, not Coca-Cola. More sugar content, say it's Coca-Cola, right?
Acha, okay.
So this is again a distribution. There is a probability function for each values it can take, right? So sometimes we have seen this, right, in our Bayesian learning. Optimal classifier is where you are trying to minimize the risk. I think we did this, but anyways, that's the idea. So one is the class you like is called the signal class. So now we'll take an example. So first example I take is I start with W equal to 0, 1 and bias term is equal to 0.5. Right? Let me just take this example number 2 and I'll solve this and it will become like crystal clear to you how to do this perceptron algorithm. So let me just paste it over here. Okay. So tell me now W. So your Y value is sine of W transpose X plus B. Yes or no? So for the points, say what points do you have? 0, 0, your actual Y, your Y predicted or sine of W transpose X plus B. So what is the 0, 0, 1, 0? So it's a OR function, okay? 0, 1, sorry, 0, 1 and 1, 1, right? So this is 1, this is 1, this is 1, this is 0. So now presently, what do you have for the value of the first one? Can you tell me? W is equal to, I will take 0 into, so your Y is equal to sine of 0 into X plus 1 into Y minus 0.5. Yes or no? This is the value you want to take. This is your neural network, your perceptron, weights, W transpose X plus B. Clear?
Yes.
So now for 0, 0, what is it? For Y equal to 0, 0. For 0, 0, you agree it is equal to Y equal to -1 because sine of minus 0.5. So -1. Okay, I like it. So I will just put the instead of 0, I'll put -1. So for you to for a better understanding, just we have relabeled 0 as -1. Similarly, I'm going to put 1, 1, 0. So if I put 1, 0, I again get -1. Yes or no?
So it is
Yes.
mismatching now.
Yes. And I'll show you again. So this is the point. So now you see 0, 1 means which direction is the W having? In this direction? Is this your W vector, right? Along Y, you have a, this is your W, yes or no?
Yes.
Perpendicular to the line is the W vector. Okay, so we have a mismatch. So what do I do now? I do W. So my W0 was, or W0 was 0, 1, right? What will be my W1? W0 plus Y. So I'll just rename this 1, 2, 3, and 4. Y1, X1, correct? Or Y2, X2, right? Agreed?
Yes.
So what is Y? Y2 is 1 and X2 is 1, 0. So I get 1, 1. Similarly, I get B1 as minus 0.5 plus 1, which is equal to 0.5. Right? Therefore, my equation of the line is x plus y plus 0.5 is equal to 0. How does it look like? It goes through minus 2, 2, right? Right? X by 0.5 or minus 0.5 and 0.5, right? Sorry. Right? This is the intercept form.
Yes.
So my B is 1, 1. So my B is, so after this is your W1. So this is looking like this. Good. Good, good, good. Very nice. Now let me see if I am going to misclassify something. Good. Do I misclassify? So my new labels are B is equal to half. Right? B is equal to half. W is equal to 1, 1. B is equal to half. If my Y prediction is sine of x plus y minus plus 0.5, yes or no? This is true for all the positive points, right? This is from W0, W1, this will become still 1, right? For W1, this is still going to be 1. Because I have all positive values here. Just see x plus y is greater than 0 for all 0, 1 and 0, 0. For all values, this is always greater than 0 for all combinations, right? Of 0, 1s, because we have only binary values here. Okay.
So the other, like for remaining data, it is fitting though. But the
No,
first
it is
for
not.
0,
0, 0 again, it will not fit. See, because if I put y 0, 0, what is it going to be? Sine of 0.5? Yes or no?
no, I was saying that only for
Yes,
remaining
yes.
values means for 0, 0 you already tested.
No, but then you have to go back until it is valid for everybody. You have to go back. It has to. It is an iterative process. It must hold. This must hold for all.
Achha.
For W1, it is not holding now. Unless it is holding for everybody, you are not going to stop. So this becomes now +1 under W1. Now you see it will solve the problem. So it is a misclassified data point. So again, tell me what will W2 be? W2 is equal to W1 plus X1, Y1. Yes or no? What is X1? 0, 0, right? Y1 is -1. Correct?
Yes.
What is B2? Is equal to B1 plus Y2. Correct? Or Y1, sorry. This is 0.5 minus 1. Yes? So now you see your
Yes.
equation becomes x equal to 0.5. So it is x by 0.5 plus y by 0.5 equal to 1, which means this line now absolutely correctly categorizes both, right? Now you see you have this line. Forgive me for my drawing. Negative, positive, 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 right? So
Yes.
this algorithm is always known to converge. So I will. So is the algorithm clear? So this algorithm is always known to converge for linearly separable data. Let's see why. We'll prove it now. But it is not true for linearly non-separable data. We'll also see that. For example, the ZOR problem. It's a very famous problem, and that will lead us to an artificial neural network or a multi-layer perceptron. Okay. So let's prove that proof of perceptron algorithm always converges. So how will you prove it? So I'll give you some notations. First notation is, what did we learn? Say W star. Say W star is the optimal classifier. So what do I know? What is the norm of W star? It must be a unit vector. We discussed it. If it is not, we can just scale it back. Correct? It will not unsatisfy any of this constraint. Correct?
Yes.
This is one of the properties. Second property, W star transpose xn yn, right? Should be always greater than 0. And we'll just put a threshold, say C, right? Because all the positive points will be categorized in one side, one negative points, and all the positive points in on another side. Yes or no? And say the minimum distance that you have is C. Okay, this has to, C can be in the minimum 0, like tends to 0, right? There should be a constant C.
Yes. Now, one more thing
Yeah,
means that norm part equals to 1. That was not needed to be done. Means the scaling part was not needed to be done in the last question.
it was not required. It is not even required any time, but it is required to prove this because we have this idea of what is it? We are scaling this because we want that this D to be dependent only on the W transpose X, right? But at a particular moment in time, if you divide by a constant, it is not going to change the sign of the things, right?
Yes.
So does not really matter, but for the proof, it is very crucial. We'll see. It's a very, very nice proof. So how can we prove this? So the idea, remember these 2 points, we'll be using them critically. So what do I know? I know WT plus 1 is equal to WT plus XY, right? If X is misclassified. Do you agree? We know this.
Yes.
Now, if I just take W transpose, or WT plus 1 transpose W star, and I take WT transpose W star, what I plus Y W star transpose X. What will happen to this? Do I know about something about this? I think you'll be able to tell me. There's something that you know about this.
Means like greater than sign will be positive.
Good. So this will be, this is greater than C. Do you agree?
Ha ha ha. Yes.
Very nice. So you can write this as greater than. So this is greater than C. So this term has to be W transpose. Tell me if I write the inequality correctly. Yes or no? Because I'm going to lower bound this by a lower term on the right hand side. Right? Because my left hand side has to be greater than that. Do you agree?
Yes.
I keep on doing this. So I replace WT as WT minus 1 and X all of these. So by induction, do you tell me, do you agree that I will have W0 transpose W star plus TC? Because I can replace this by the same equation. If you're not following, I can do one more step. This I will write this as WT minus 1 plus X, another X. So let me write X tilde, Y tilde, W star. Yes or no? I will get
Okay.
back
Okay.
to,
Yes.
and I keep on doing this until I get W0. But W0 I set, I have started with all zeros. So I will just cut this into 0. So what will I get? T plus 1 transpose W star greater than or equal to TC, right? This is also, we can write this as, which implies WT plus 1. If you recall your linear algebra, right? I just put a mod. Mod also has to be greater than the this. Yes or no?
Yes.
Now, if I put the mod, what can I use? I can use the rule that A dot B mod I have shown this to you, right? Is equal to the norm of A into norm of B into cos theta, right? Which means if I remove cos theta, this, yes or no?
Yes.
The Cauchy-Schwarz inequality. We proved this for a general case also. So I will get WT plus 1. This is how you must learn to prove. Once you learn to prove things, it will be like having a very rational idea. So this is equal to 1, right? Right?
Yes.
So I will get WT plus 1. I'll just keep this for the time being as some TC. Let us, this is equation 1, I'll keep. Equation 2 is much simpler than this. I will just take norm on both sides. If I take norm on both sides, what do I get? I get yes. In this equation, in the first equation, I just take norm on both sides. A square plus B square plus 2AB. Okay.
Y square equals to 1, you have put. So,
Yeah. Y square equal to 1. I have put. Y is a constant. Like a
acha,
scalar. Is a scale, not a constant. Scalar. Is minus or plus 1. So it's equal to 1. So now this term. that you have over here. What can you tell me about this? This you already know, right? Since it's a misclassified data point, has to be less than 0. Since misclassified.
Yes.
I didn't put y, sorry. I just put the y back, right? So I can again put a bound, right? Wt plus 1. And this is also another thing. Then a third condition is the norm of this is less than some r square, whatever it is. Some radius. It must not be at infinity. It must be some constant, right? It must not be, some points must not be very far away. Is that okay? When very far away, matlab, there should be a limit, even if the last point that is at a finite distance from the origin, right? It cannot be at infinite distance.
Yes.
Even the farthest point. Okay, so now I can replace this as, since I will replace this as 0, it's an upper bound, and I will replace this as r. So what will I get? I'll get, now help me in the next step. Can you help me in the next step? I have done that step once already. I can again do induction.
Acha, yes. Like it will be greater than equals less than equals to W0
Yes, so that
norm.
is 0. So t times r square plus W0 norm, right? This is equal to 0. So what do I get? Wt plus 1 squared has to be, so t plus 1, t is equal to this 0, t is equal to 0, then I'll have 1. I think I'll have to get t plus 1, right, in all these equations. So if t is equal to 0, I will get 1c, right? Just calculate the base case and let me know once. T plus 1, right? Because I have taken t plus 1.
Yes, t power plus 1 times r square.
Yes. So I will just replace this by t, and what equation do I have? I have this equation, right? Wt t, where is it? Tr squared less than equal to t square c square. Yes or no? Correct?
Yes.
This is from equation 1 and this is from equation 2. Now you see, I will just equate these two conditions. What will happen? T square c square less than equal to tr square. So t has to be less than equal to r squared by c square. Correct? Yes or no?
Is
So
how
with,
you are equating both sides.
so this is less than a particular value, right? You can use sandwich theorem. This is the upper value, upper limit. This is the lesser limit. It has to be lesser, right? Your
Acha,
Wt
yes.
is here. Your W's is here. More norm of W. Your t square c square is somewhere over here, which grows like this with t. So let me just put that graph. Your sandwich theorem idea that you used to use all the time in your school. Wt, then you would have t square c square, and you would have tr square, right?
Means that as t tends to infinity, both becomes equal. Means sandwich
Not
theorem.
even infinity. That's the idea. It will be in finite steps, because you see after, so r, right? R is fixed. So your C value that you have R square by C square, this is finite, right? This is a finite value. These two are fixed values. T is, you not put, T is less than infinity for sure. So between T is less than infinity, both will become equal, right? Both will become equal. WT has to be equal to them and it cannot change after that, right?
Yes.
By Sandwich theorem, it has to be, it cannot change. So it has to converge in finite time. And that exact value I know, R square by C square, the largest data point by what is the minimum gap that the optimal classifier with the model. Okay, so it has to converge. Any questions regarding the proof? Okay, if there is no more questions, now let us go to the drawback. So I proved this and I'll now show the drawback. We will go into neural networks. So I'll do it at the end. So the drawback is what is called as a XOR problem. So 0, 0 is 0, 1, 1 is 0. We have seen for non-linearly separable data points, this will not converge because you will not have those conditions, right? That we took in the beginning. 0, XOR 0, 1. This is your 1. Correct? All the conditions that I took greater than C will not hold. If it is the data point is something like this, will it hold? There is no line that separates these two linearly.
Yes.
So now you see there is no single perceptron. But there is one idea that I can use. Because this is not linearly separable, because you see these two belong to this area, right? So I would want a class like this, classifier like this, yes or no? Where this part will be positive and this part will be negative. These two parts. Yes or no? So in this case, one hyperplane cannot do that, right? Can't do it. Can you do this with one hyperplane?
No.
So how many hyperplanes do you need? You need two hyperplanes, right? If I have two hyperplanes, I can take things in between these as one class and outside these as other class, right?
Yes.
So we need multiple perceptrons somehow. And how we're going to get it, we'll see now. Multiple perceptrons, and this is where MLPs come in, or multi-layered perceptrons, which is today in deep learning literature called feed-forward neural network. But these foundations were all laid very, very early. It was laid in 1950s, but people couldn't do successful things with this because you did not have compute, right? So now give me one example. I'll just very simple neuron. So see, I have X and Y as my inputs, right? Okay, I have these two as my inputs. X, Y, 0, 0, 0, 1, 1, 0, 1, 1. What is the out? Okay, let me take X1 and X2. What is the value Y? 0, minus 1, 1, 1, minus 1. Yes or no?
Yes.
Okay. So I want to first represent one hyperplane that says that this plus is minus 1. This is me write this as minus 1. So let me try to make one hyperplane. and everything to this side is +1. Okay. Okay. Clear?
Yes.
So how can I do that? Very simple. This line, if I take, I'll be able to do it, right? Let us take that line. I will take, so again, I'll put one neuron here, that as I had shown. I will write Z1 as sine of half minus x minus y, right? Is it okay? I think not okay, right? 0, 0, it should be 0, 0 should be -1. So it should be x plus y minus half. Is it correct, right? This is the first neuron I'll have according to my wish.
Yes.
So now you see this will categorize as, so I will write outputs of Z1 for your understanding. What is the outputs of Z1? Tell me 0, 0. যদি আমি দিই তাহলে কি হবে? Is not x1 plus.
-1.
Good. 0, 0 minus half minus 1. So okay. So 0, 1 is 1, 0. So this is sine of 1 plus 0 minus half. This is equal to 1. Right? Similarly, this is also 1. This is equal to 1. Yes. Whatever I wanted, I got.
Yes.
I want another hyperplane now. That will say, what will that say? So this hyperplane, that will say this side is negative and the other side is positive. So this hyperplane will say -1 +1 +1. How do I just give me? I'll just write a better notation, color notation. So let me take one hyperplane, this hyperplane. Just to draw, put shades is better. Okay, this hyperplane will say -1 +1 +1. Right? This hyperplane will say -1 1 1. Okay, right? This is what we want. Okay, I have put both the hyperplanes and their corresponding colors. Both +1 will give me the intersection region, positive and negative will give me non-intersection region, right? So how do I get the second neuron, second hyperplane? Z2. Z2 will be what function? Give me a function.
For the 3/2 minus x1 plus x2.
Good. So I will take Z2 as sine of, so 3/2. So in the case of 1, 1, I want it to be negative, right?
Yes.
Right. So minus x minus y, or minus x1 minus x2. এটা বললি? So now you see if I put one negative point, so 0, 0, it is sine of 3/2. It's 1. Whatever I wanted, I'm getting. 0, 1, that is half, so it is 1. This is also 1, this is half. This is -1, right? So I'll just put it in the brackets if you're not following. 3/2, half, half, minus half. Minus half, 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 3/2. Okay. Now give me the intuition. How will I merge these two? Can I do something like this? Z1 plus Z2 minus 0.5 sine is equal to output. If I do this, what will happen? See, Z1 plus Z2, if it is opposite sign, it will become negative, right? Same sign, it will become positive. You are following? I'm waiting.
Acha, means can you tell me what is the motivation behind doing minus 0.5?
See these two, because these can be 0, 1, 1, 1, 1, 0. Oh, because Z1 and Z2 can be plus 1, minus 1, right? Plus 1, minus 1, correct? See what are the values it is taking? It can be either plus minus 1 or two positive ones, right? It can never minus two minus ones are occurring together, right?
Yes.
So if it is opposite signs, I want it to label as negative point, right?
Yes.
So if I want to label as negative point, these Z1 plus Z2, because I put weights to be 1 and 1, will cancel out because it's plus minus 1.
Acha.
For those points, I want to add a negative term. But when if it is both 1, then I can, like, you can also subtract 1 in this case. It doesn't really matter, right? 0.5 can, you can take anything. Take 1 also. 1.5 also. Doesn't matter. Up to 1.99999, everything will work, right? Isn't it? Is it clear? So you see, when you put multi-perceptrons together, they already automatically solve for the non-linearities in the data. They will change, they will learn in a way that it will categorize the non-linearities in the data into another level, and then it will make it linearly separable finally, and then you will be able to separate it. Okay. And this can be learned in closed loop. We'll see how to do that today. In the next half an hour, we'll complete that. Is that clear to everyone? Is it okay? Can I go on to what is feedforward neural networks in the modern sense?
Dada, can you explain that minus 1 comma 1, 1 plus 1 comma minus 1 in those ordered pairs in the diagram?
Which,
Then
oh,
diagram part.
so diagram this blue color. Look at this blue color. This is your, you understood the choice of the weights and biases, right? Weights and biases which took here.
Like the means the equations x1 plus x2 minus
Yeah,
half,
yeah,
that one. Yes,
yeah,
yes,
yeah.
that I've understood.
So I have two weights, right? At the original case.
Yes.
So now I am saying in one weight it is not going to happen. So for these two weights, they will be separating it into two hyperplanes, right? Two different hyperplanes, they'll separate it out, a positive
Yes.
side and a negative side. So I want the negatives to have opposite sides and the positive to have the same sign. That's the idea. So in one side, just see in one side of these will be negative, right? So the blue ones, on this side it is negative, on the or below side it is negative. For the blue one, everything above it is positive. For the white one, everything below it is positive and everything above it is negative. Clear?
Acha, means like so that you can distinguish the points. Plus 1 and
Yes.
plus 1 means positive.
Positive.
Only.
Plus one means positive. Negative one, positive one is negative. This represents negative. This represents negative. This represents positive. If it is very clear, now let's see how to learn these. So in today's sense, we do not use the sine function anymore. Instead, we use something called as activation functions. They're much well behaved, have better gradients and so on. So let us take a few examples of activation functions first, and then we'll formalize what is a feed-forward neural network or a multi-layer perceptron in today's day and age, which when you write in Kera's dense layer, what does it mean? Okay, let's see. So nowadays, to bring in non-linearity in the data, do you agree these were all non-linear functions? Can you make a non-linear function out of linear functions? Only linear functions. So you take W transpose X plus B, had the sign not been there, this is the non-linearity, because this is, you have a function like this is a non-linear function. Right? You cannot write this as y equal to mx, right? This function.
Yes.
So whenever there is a non-linearity, this algorithm, what it does is, say this data is like this. There are some websites on the internet, please go and play with it. You will be able to see how it changes its weights and biases to, I can share that internet on the Teams group as well. Let's not naming it just in case there's some copyright issues. So they will automatically make these complex decision boundaries because it is actually transforming it into a linearly separable space. So in the original space, it has to be very complex, right? Like this one. So we have to have some linear, right? We need to have some non-linearity. Why? Let us see an example. Say in this function itself, say you have one equation y equal to ax plus b. Okay. Why non-linearities are essential? Non-linearities are essential. Please follow it. Very interesting math is coming up. Y2 is equal to, say, cy1 plus d. Okay, so this is you. Do you agree? I take x, I pass it through the first neuron, neuron 1, and then I pass it through second neuron. Right, this is my first neuron, which is A and B. Second neuron is C and D. Right? From now onwards, you should be able to understand this notation.
Yes.
So x is my input. Whatever I'll get, y1 here is my output. Okay, now you see if I write y2, can I write this as C of ax plus b plus d?
Yes.
So what does it mean? It means cax plus bc plus d. This is essentially equivalent to saying x is an input to a neural network which has ca as weights and bc plus d as the biases, which is again you can relabel this as m and n, right? So this is again linear, right? So function, linear function of a linear function is a linear function. So you will only be able to separate linear data points if you take only linear data, right? Do you agree? Linear functions can only separate linearly separable data points. Okay.
Dada, one more thing to ask. The means function data, was it linearly separable or non-linear? Means we
You can
took two
see
linear
it is,
lines.
so it's piecewise linear means it is non-linear. Linear is one linear function. So it's not linear, right? You can clearly see. That's why you couldn't say
One line don't work. Yes.
exactly one hyperplane won't work. That's why you require this complex decision boundary where you have this closed loop and all, right? In that way, though, you can put any curve as linear function, sum of linear values, right? You take a circle that is also linear, linear. But that is not true. I'm just saying one linear hyperplane, right? So is this clear that linear functions can only produce linear functions? Composition of linear functions can produce only linear functions. Yes or no?
Yes.
So therefore, it is not useful to have linear compositions. Therefore, in neural networks, we saw we need an activation function, right? Like a sign. So this is called an activation function. So in neural networks, it's very simple. The idea is pretty simple. I'll just draw it over here. The idea is you have these inputs, right? X1, X2, Xn. You have hidden layers that will compute some features. It will be learned on this will you will not do anything. Algorithm will learn it. We'll see how. All of this X will be fed to all of these data points, like we fed it just now, right? Clear? And then again, these will be fed to more layers. Finally, you'll get an output layer. This is your prediction. So let's take an example with 3 inputs, X1, X2, X3. Say we have 3 hidden layers. Okay. So now we have 2 hidden layers. Then finally say you have an output and say this predicts cats versus dogs. +1, -1 or 0, 1, whatever we want. We'll see how to do that. Right? We already know these functions. Do you agree? This we can do. This is very much like the activation functions that we learned. Okay. Like not the like the sign function and the XOR function XOR case we learned, right?
Yes, but much more complicated.
You can, so you don't need to think about what weights you're going to give. That the algorithm will learn for the data when it gets the data, but you are understanding this right idea. So if I have say a 128 by 128 image, or say 28 by 28 image.
Dada, like, can you explain what does the next layer is where we have two uh, neurons that does means
This
why
will
we are
take
having
this
two,
will
three, four in the second
that
layer.
is that is a design parameter. We can have hundreds also, hundreds, 30. We can that is a hyper parameter you have to tune. I'm just giving you an example. We can have 3 and then 1 layer output also. That is, with experience, you will be understanding what is the design that you want for your data. More data we'll see next class is more deeper networks, large, more neurons, more complicated data, more neurons, right? Clearly, if you have more data, you can represent more neurons, you can represent more complex functions, right? Clearly, if in that, if you had like 3 data, you could have had another hyperplane, right? Something like this. You could have had another hyperplane. N data points could have just had n hyperplanes, and you could have a combination of all those decision boundaries to give you positive and negative data points, right?
Yes.
That's the idea. So you can, that will be learned. We'll see how to do that. But what are the activation functions that are used? Activation functions are, we'll see now. But first tell me what is an output of a, so let us take the activation functions first. So these are non-linearities introduced to MLPs. So we do not take a sign activation function. Can you tell me why? Because that is constant derivatives, right? It's very difficult to take like derivatives of this function, right? So this is you can take that function like sign as an activation function. You will see what you will get the derivative as. What will you get sign activation function as derivative as? Sign of x 0, right?
Yes, constant.
Sine of x is equal to derivative of sine of x is equal to 0 if x not equal to 0, not defined if x equal to 0. So this is not a good activation function. Do you agree? Because derivatives is what you have to deal with, right? For optimization, we have seen that we need to take derivatives of functions. because we need to grab the gradient descent, right? So some good
And
activation.
one thing to clarify, x1 to x10 are the points. So
x1 to x10.
x1 to xn.
Yes, there are features. So for example, you can have many such points. I'll clarify. I don't want to worry about data points now. Say 28 by 28. It is 784, right?
Yes.
60, 50. I guess it is 784, right? Yeah. So you can just take 780. You will have 784 features or image. This is an MNIST data set. And you will feed it, say, to 100 layer. You will convert it into a 100 layer neural net, 100 layers. So you will convert it to say 100 now. So how will we do that? We'll see in some time. And then say you will reduce it to 62 or 32, and then you say you reduce it to 10. 0 to 10, it is going to classify. MNIST dataset has handwritten digits. I'll give you this as a assignment problem where you'll have to classify handwritten digits using artificial neural networks. Okay. Good. So some cases of non-linearity is this. We have already done this, right? It is used generally at the end. Why can you tell me? You have seen this is the sigmoid activation function, right? So x greater than 0, sigma of x would predict class 1, x less than 0, class 0, because greater than 0, this is greater than 0.5, this is less than 0.5. Yes, we have seen this in logistic regression.
Yes.
So take a derivative of this. What will you get? We have done this as well. You'll get 1 by x squared e to the power minus x. Yes or no? By chain rule, which I can write as 1 minus 1 by 1 minus e to the power minus x squared minus 1 by 1 plus e to the power minus x, right? Or the other way around, which is equal to sigma x into 1 minus sigma x. Do you agree? What is happening, right?
Yes.
So this is less than 1. Do you agree?
Yes. Yes.
So what happens when more layers are put with this sigmoid activation function is you will have products of these. We'll see. So more layers, you will end up having sigma x. We'll see why, but remember this in mind. Sigma y you will have. So this goes to 0, right? We'll see why. If there are many sigmas, you will go to 0. Yes or no?
Yes, because less than 1. So
Correct.
Point.
So this is why this makes training neural networks slow. Same is for tanh function. Tanh function you can see e to the power x plus e to the power minus x. How do you know? How does tanh come? Like how is tanh
No.
defined? Okay, so let me I'll just give you two bad activation functions which should not be used internal layers like these, and you can check out ReLU, leaky ReLU. These two you can check out. This is for your homework. Okay, so this you should not use. So these should be used at last layer only, because you may want the outputs between 0 and 1, right? For a prediction of a class like dog versus cat. Yes or no? Similarly, you can also have softmax in the last layer, and we have done softmax regression, right? So last layer can be like a regression, where the penultimate layer will give the features to a regression problem. Just go back and see logistic regression, you will understand. Where in logistic regression, what was happening? We were giving data to the last layer, right? Directly. And this was predicting feature 1, class 1, class 2, class K. This was your softmax regression. But anyways, we'll not go into this for the time being. You can just see the class where we did softmax regression and logistic regression. The last layer, I'm telling you, can be thought as a linear regression or a logistic regression or a softmax regression. If you are following the classes, then I think it is clear now. Otherwise, you have to go back and see once. Okay, maybe I'll explain at the end after I explain this activation function. So what is sin x? How can sin x be written as? Can it be written as e to the power of ix minus e to the power ix by 2?
Using De Moivre.
Yes. So can I write, so sin hyperbolic x is written as e to the power x minus e to the power minus x by 2. So that's how you define tanh h. Right? Same idea. Without the De Moivre, only real numbers define this tanh h function. So can you tell me what from between what values this tanh h functions can range between? I know sigmoid function how it looks like, right? It looks like this. 1, 0. It looks like this for sigmoid function. But tanh h function, how does it look like? Very simple. For e to the power minus infinity, what will happen? This will go to 1, minus 1, right? E to the power tanh h of 0. What is tanh h of 0? 1 minus 1,
0, 0.
0. Tanh h of infinity, it is equal to infinity by or e to the power x by e to the power x. 1, right?
It's like the sigmoid only.
It is like the sigmoid function, you're right. But it is between 0, minus 1 and 1, right?
Oh, ha. Yes.
Sometimes when you normalize the data between minus 1 and 1, then you can use tanh h at the last layer. RNNs use tanh h. In whatever chat GPT you're using, they use a tanh h function at the end. Okay. So tanh h. So derivative of a tanh h is an important, interesting thing to see. Can you do the derivative quickly? E to the power x minus e to the power minus x whole square minus e to the power of x plus e to the power of minus x whole square. Is it correct? I don't think so. This should be plus, this should be minus, right? Right, u by v rule. I take the derivative of the numerator.
Yes, okay then. Yes.
And then multiply the denominator. So what do I get? I get tan h. So sorry, plus in the denominator 1 minus tan h of x whole square. Yes or no?
Yes.
So this is also less than 1. So again, I cannot use it because it will become very, very slow, and we'll see why low gradients are a bad problem for neural networks. But therefore, these people recently came up this activation function called rectified linear unit or ReLU, right? And remember, don't forget the big picture. The big picture, what is the big picture? Can you tell me? The big picture is trying to always add a non-linearity after a linear computation, right? Because all my linear are W transpose X plus B, but I want to add a non-linearity on the top of it to model complex functions, right? Any questions?
Can you means explain that non-linearity from the point of diagram?
I will explain, but I'm just talking from the point of the XOR problem, right? In the XOR problem, we
Acha.
introduced in the non-linearity, and then we saw we were able to solve it. But only W transpose X I was not able to solve, right? Diagram I'll bring.
Yes.
So ReLU of X is X if X is greater than or equal to 0, 0 otherwise. So this function looks like this. Correct? If you're
Yes.
free, people who are free now, please tell them if you can see the other functions, they're more even more efficient. Okay. So the derivative of the ReLU of x, shouldn't write partial, it's not required, is equal to 1 for x greater than 0, and I'll define 0 otherwise. Right? Because at 0 it is not differentiable, but I will say at 0 it is 0, the derivative. Okay, I can do that because 0 is again between these two lines, as I was telling, it's a subgradient. Okay, this is true, this is the derivative. But now see the derivatives don't vanish, right? This ReLU, if I keep on multiplying, this will still become 1, right? It cannot go to 0, provided that there is a negative point. We'll see in those cases, for those data points, you will not have any update. But if it is 1, it will not vanish, right?
Yes.
So where is the non-linearity? This is because this is piecewise nonlinear. So this is the non-linearity that is being brought in. Okay, now in diagram perspective, as you were saying, now we will be seeing how to learn these neural networks and what are the fundamentals. So if you have cleared about it, so let us see. First, let us define one neuron or a layer of neurons. Let us define a layer of neurons, say layer L. So layer L will have output from which layer? Right. So okay, if you're not following, I'll just go back to the diagram that I drew. Okay. So these are your features. Okay. These are your input features. Okay. Next, I have one neuron. Consider one neuron. This neuron. Okay. This is the first layer. This is layer 1.
And Dada, are not you sending the labels for the training data?
We will see what we are not going to send the labels. Why we'll see. Labels is what you want to predict, right? If you send the label, the function will just give you the labels directly. It will just give ones for the labels and 0 for everything else. You want to predict the labels. Why should you give the model the labels?
Okay, okay, okay.
Isn't it? In our logistic regression also, what were we doing? We were taking one neuron. And then what were we doing? Remember why I said it is a last layer is a neuron. This was our logistic regression, yes or no? We showed this using MLE estimate x1 to xn, right? See, it is a single neuron. This is your activation function, yes or no?
Acha, acha, yes, I remember.
Now this is where, that's why I told that time that you will do when in the last layer is 10 classes, we did a softmax regression. Do you remember? E to the power of W transpose X plus B by summation of for all the WIs, right? So you had different WIs, W1, W2, WK. This was your
And we will take
probability.
the maximum one, and that
Yes,
will
yes.
make a
So this is
predicted class.
because but at the last layer, the features are coming in a neural network. The features will be computed by the neural network. In reality, what you do, you feed the features directly. But in a neural network, you can think that a neural network computes the features so that the last layer can predict according to the type that minimizes its error, right? So this is features. Maybe a neural network is finding it, or you are giving the features directly, then it's a softmax regression problem, or a neural network, that's a neural network problem. Same thing, we'll see. But layer 1 you understood, right? These are called layers stacked one after the other, just like the XOR case. Okay. So let us say that we have L layers in the neural network. NL is the number of neurons in the Lth layer. WL is the weight of the layer L. ZL is the output of the layer L, or let me write VL as the output of the layer L. And ZL as some activation function f into VL of VL. Okay, we'll see all these things. What are these? So I will draw one neuron for the time being, and then I will explain all of these. Say one neuron. So I will draw NL. This is the previous layer, L minus one layer. So how many neurons will it have according to our definition? In the L minus one layer, it will have
NL minus one.
Number of neurons will be L minus one. So L minus one features. Okay. So these will give me output of. Now I'm going to consider layer L. And I'll consider one layer. So it has L layers in this neuron now, in this layer. Okay. Clear? For this output, again, if I ask you, so say f is the activation function of this layer. What can I write? The output. So first I will write, say, without the nonlinearity. And that I'm representing as VL for one reason. So this is the ith neuron.
Can you
What?
explain from this Lth layer?
Yes, I'm doing that again. So
I was facing some network issue.
Yeah, sure. So the previous, think of this, the previous layer can be input features also, or some intermediate layer. Can be input features or intermediate features. So every neuron in this layer, in this next layer, NL layer, will get all these previous layers outputs, right? Yes or no?
Acha, yes.
So you will have V. So say this is the ith neuron. So VI, okay, of the Lth layer. So I am putting the Lth layer on the numerator will be equal to, do you agree? Summation of. So I am considering one data point for the time being. You can add all the data points at the end, overall data points. But for the timing, let's have one data point. W. So this is W layer L. This is the layer L. That is the doing the transformation. Okay. WL JI Z L minus 1. Sorry. ZL minus 1I. Right? I equal to 1 to N. Yes or no? Plus BJ. Similarly, VJ or ZL will be. So these are the computation at a layer. This is a neural network. That's it. Okay. This is the non-linearity. Are you following? So yeah.
V was the input of layer L or output?
Which one? V.
V.
So this, consider the ith neuron. Ith neuron takes ZL minus 1, 1, the first feature, ZL minus 1, 2, dot, ZL minus 1 in L minus 1, right? So these many features you will have. This neuron will take, and I will just do, say this is the ith neuron. So what will I do? W or the jth neuron, they say this is, I'll not write, let me write J here. I think that's why you got confused. Jth neuron will be J1. See, there are multiple neurons, right? That's why there's a problem. I'm writing J. If there was one neuron, I could have just written W1. Right?
Acha. Yes.
Now you will understand this entire thing in a matrix form, right? This is also can be written as a, so for all the j's, I can stack them together, right? So now I will say that x, I will write as, I'll stack the data points like this. x1, x2, dot, 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 xn, right? So this is, if there are f features, this is n0, n0 cross n, yes or no? Right, the zero, this is the input features. Okay. Is it okay?
Like capital N features and N0 examples, training
No,
examples.
n is the number of examples. These are the data points. Xi is a n0 dimensional data point. Just to keep same notation, I could have also taken d as the dimension. This is equal to d. Okay, I'm stacking the data points vertically instead of horizontally, as we have been doing till now. This will give us advantages, right?
Acha, okay.
So now in the layer 1, right, I am taking input as some r n0 cross n dimensional feature, right? I want output as n1 cross n, yes or no? I want, there will be n1 neurons, 1, 2, dot, 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 n1, layer 1. Agreed? How will I do this? How will I do this? I will do this by v1 as, what will I do? W. Can I do this? X w plus b, where w will be, you can also write x on the right hand side. So w x plus b, w, this is n0 cross n. What will be the dimension of w? n1 cross n0, right? Yes. And this means that I will have b written n times if there are n data points for the same, because bias is same for all the data points. Okay, did you understand? Now you see this v will be our desired shape, yes or no? So I have n1 neurons. So v will be,
Bias thing I couldn't get.
biases are fixed, right? Biases are fixed. It's a scalar instead of vector, right? Here you are getting w transpose. So I'll just write it down. Your w transpose zi or z l minus 1 plus bj. This was your vj. This was your vj. So this is a scalar, right? For n of these, you will have 1 to nl of these.
Acha, okay, okay.
So
For one neuron, one bias.
exactly. So when you're multiplying these two, this is nothing but a, what is this? W11, W12, dot, 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 W1n, N0, W21, W, this is what I'm writing once so that you can remember, dot, 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 W N1, 1, W N12, dot, 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 W N1, N0, right? This is N1 cross N0 matrix. See, you have N equations, N1 equations and N0 unknowns. That's what we wanted. We wanted the neurons to be fed to this N0 unknowns, and we wanted an N1 equations. Each of these equations is given by one of a neuron, right?
Yes.
Clear? So if this is clear, okay, just yeah. So each of these will have, so B1, B2 dot 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 Bn1, right? But you will have n data points, so you will have to add them to all of the data points, right? This is why I'm saying you will broadcast it. Whenever you have n1 cross 1, and if there is a repeated dimension and you have an added sign, this is the Python notation. You can just broadcast it into all of the training examples. That's what Python does. Okay, NumPy does. We have seen that before. Right? When we add a scalar to a vector, you will just add them as it is. Right? This is n1 cross 0, right? N1 cross n. You add a n1 cross 1. So what you will do is this, you will add this n1 vector with all of these n.
Acha, acha, acha.
So now if you have, it is clear to you, now your ZL will be just the point-wise activation function of VL. So your neural network, feed-forward neural network, feed-forward neural network. What will this be? Your feed-forward neural network will be for each layer, layer L. What you will do? Tell me what you will do. So now you
Like
need not
for
think.
each neuron.
Wait, now you need not think in terms of one neuron. You can think in terms of one layer, because I have written a vector notation, right? I've written it in terms of a vector. Say your X is R n0 cross n. So for layer L from 1 to capital L, right? So you have L layers. What will you do? You will do VL as what? And I will set Z0 to be equal to X. W L into ZL minus 1 plus BL. Yes or no? And you will do ZL to be function of WL, VL, only VL. And this will continue until you have the output layer. Clear? So for example, you have this input X. This you will feed to layer 1. Layer 1 will give to layer 2. This is done by, say, W1 B1, W2 B2, and this will give me your Y output. So your ZL is the output. Okay. You can put a different activation function in each layer also. I'm just putting an L there. Clear? And then at the end, what will you have? You will have a loss of ZL, capital L, and the labels Y. Yes or no? And then you have to train W's as W minus DL DW. This is the gradient descent, right? And how we'll do the gradient descent, we'll do it next class. We don't have that much time, but I will give you the foundations of gradient descent today, and then we'll continue next day. Okay. The formal
Like
path.
one thing, last layer will have one neuron or more than one.
So if it is a softmax, it can have n layers depending on the output, right?
Acha, acha.
If it is one layer, it's a classification between two classes, then one layer. If it is MNIST, then 10 layers, right?
Okay. And one more thing, here we have to learn W and B, and
yes.
F is fixed, or if we have to learn F
Fixed.
also.
F is your design, fixed. How can you learn F? F is a function, right? You can learn it, but not here. It's a design choice, like ReLU. F is the ReLU thing. We'll see how these gradients will add up. But the feed forward is clear, right? So you just see ZL minus 1. What is the dimension of ZL minus 1? This is NL minus 1 cross N. Yes or no? Do you agree?
Yes.
And this is also NL. This is your NL cross 1. Yes or no? Because this is also layer L. This is NL cross NL minus 1. Please remember this notation. The number of layers output. So if I ask you, layer L has, very important question, it can be asked in gate, has 100 inputs and 64 outputs. Then find the number of parameters, of trainable parameters in L. Tell me the answer. So input is to this layer is 100 dimensional. Output is 64 dimensional. Tell me, what is the W dimension then?
Acha. Then it should be 100 cross.
Okay, my Z is 100 cross N. Whatever, I can put one also, one data point. So what should be my W? This is your L minus 1 layer. What should be my W dimension so that I get?
Okay, 100 cross 64. Sorry, 64
100
cross 100. Nah, from 100 to 64.
64 equations, 100 unknowns. How many plus? Plus
B100.
64. Each of these neurons will have, so 64 is the number of neurons in this layer, right? The number of outputs is equal to number of neurons.
Yes, yes.
So number of parameters will be 64 into 100. Plus, you said you will learn B also, plus 64. 6400 or 6464, right? Agreed? So if you have n layers, you have to add up all these weights. So that gives you the total number of parameters of a model. More the parameters, more complex functions that you can train. We'll see that in next class when we do this idea of bias and variance. This idea is clear, right? So what?
Yes.
So feed forward, we have been able to do, but how do I train these Ws? Write down the, so there was a very nice paper by Hinton in 1994 in Nature, maybe, that gave us this algorithm. So this algorithm was not there. See, he just used Newton's laws, but Newton's calculus, but people did not even think of this in this sense. Therefore, you couldn't use back propagation to train neural networks. So the idea is, do you see that you have layers, right? You have to train back propagate the loss through all these layers. You have to do the update through all these layers, right? So you have to do Wij L for all IJL. You have to do this, right? When you're training them. This is a non-trivial problem, right? Because it's that so many compositions are there. Each depend on compositions of others, right? Isn't it?
Yes.
So how will we do this? So for understanding that, let us understand one idea. That is the chain rule. And we'll stop after chain rule in multivariate calculus. Say you have a function f. Say you have a function f, which is, I'll give you a very nice similar example to us. Say you have u and v as two variables, right? Two features, correct? I think you have done multivariate calculus, but I'm just going to give you, in case it's not that clear, I'll just inform how to infer multivariate calculus from a univariate calculus sense. So say I have three functions now, x, y, and z. Say if y and z can be some functions of force. They can be force vectors or acceleration vectors. And x, y, z say gives you the position of a particle. Okay. And say finally you have a function f that takes all these together. So I have function f of x, y, z. This is some function f is equal to some say let us write so they say this is some quantity p, right? Or let us write this as quantity l. Okay, but x is a function of u and v. What is a y function of u and v? Z a function of u and v. Is the problem clear? And you are
Yes.
told to find dl du. This is the exact thing that you have to do in the neural network. Find dl du, right?
Acha, like with respect to first layer, what is the loss?
Yes, because not in the first layer, all the layers only you have to find, but at the end of the day, you have to go to the first layer, right?
Yes.
But you see, if it was normal calculus, I could have done something like this, right? dl dx into dx du. I could have done this if it was normal calculus,
Yes.
normal chain rule. But it is multivariate calculus. What does f change in f depends on three factors. So let us take three factors now. Understand three factors. X, y, and z. Okay. Delta x, delta y, and delta z. You see this delta x, delta y, delta z. To see the change, actual change of the function of L, we have to see all of these changes separately, right? Or you have to see the change along this vector, which is difficult problem, right? So in the first order terms, it is essentially seeing how does f change when you change x delta by x by delta x, y by delta y, and then z by delta z, right? You essentially reach this point, yes or no? Right?
Yes.
So your delta of f, which is approximately equal to what? F of x plus delta x, comma, y plus delta y, and z plus delta z minus f of x, y, z, which is nothing but x plus an x vector plus delta x vector, right? You can put this x's together, x, y, z, and delta x, delta y, delta z, right? Yes or no?
Yes.
So you see this is a non-trivial problem that we are solving. Seeing changes along three directions. So to do chain rule, what do we do? We have seen partial derivatives, right? We can fix all the other coordinates and just move along x. For well-behaved functions where derivative exists, the first order Taylor expansion will give you this value. So you can write this as delta f as approximately equal to delta f delta x del x plus delta f delta y del y plus delta f delta z del z. This is nothing but the Taylor series, right? We have written this in a univariate case. This is a multivariate case. Since I'm writing delta x, delta y, delta z. Okay. So you see one thing. So it is like taking the derivative along x and see moving along delta x, right? That's how you would move around. Well, how do you write delta y? You write dy dx into delta x, right? When you you try to approximate a change in y with some delta x with a derivative value at that point.
Yes.
You try to move along the tangent of the value. So you try to move delta y as dy dx delta x. Here also is the same thing. That is also nothing but a Taylor expansion, right? I'll show you the 1 degree, then you will understand. Wait. This is what you do. So now let us derive the formula and then I'll show you why it is a Taylor expansion in 1D. And all Newtonian derivatives are actually Taylor expansion in one with one coordinate, like this linear term. So if I just do delta U now, can I do this? And then I put limit U tends to 0. Our normal calculus ideas. And then I will have del F, del U as Olefal.
Acha, del F, del Y, del Y, del U.
This is your multivariate calculus chain rule. So whatever function a function in turn depends on, you have to change all those functions and then again change those functions and take the sum of all the products instead of one value. Similarly, for V also you can write. What will be the V? Can you tell me?
Del F,
What
del
will
X, del X, del V.
del F del X, del F del V plus dou F dou Y, dou Y dou V plus dou F dou Z, dou Z dou V. This is exactly what we'll do next day in back propagation, and we'll see there's a very intelligent way to do this in a neural network. But before we end, I promised you about the chain of the Taylor series. Just look at this.
Or
Right?
dou F, dou V, that will be dou X, dou V. First term.
Sorry. Dou X dou V. So now tell me, I derived the Taylor series for you in the first class. What is the Taylor series of this?
Is Fx plus
F dash X delta X
y1
plus.
factorial is double dash X del X square.
See, all these terms will ignore when limit delta X tends to 0. So you see, now if I put delta X this side, Fx plus delta X minus Fx pi delta X is that F dash X. Approximately equal, right?
Acha, the definition of derivative.
Exactly. From the Taylor expansion also you can get, or in other words, your delta Y. This is your delta Y, right? This
Yes.
this is your Y. This is your Y new, Y old. So this is delta Y is equal to F dash. This is why you write this as. Similarly, this is also exactly the same thing. If you write it in multivariate calculus terms, you can also do that. So the idea is you need to know a little bit of more multivariate calculus, multivariate Taylor series. So you just be able to write this. It's the same thing. Clear? And we'll see how to use this. So any questions regarding the forward propagation, how we convert these features to outputs? The training we'll be doing in the next class. Yeah, I thought I'll complete it today, but okay, it's good to go. We'll finish it up next day and go to understanding what is biases and variances and so on. Okay. So should I stop? Any questions? Okay. No more questions. Just stop recording. Okay.